we reflect all of these. So now the point I mentioned for a while back what the dictionary was. These operators, they correspond to the free-form fluxes on the 5-sphere, and the 5-sphere has no free cycle, so these are not, hypological or monopole, just sometimes, dipole free-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down an effective 5-dimensional theory with this mode, and then solve it. And it's really magic because there's no symmetry that would prevent this. The bigger mode here, some harmonic on the sphere, it's not lower in energy than the other harmonic by a lot. Symmetry doesn't keep missing with them, but there's some supergravity magic where they write down 5-dimensional runs, solve it, and then lift it to a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one massive flavor, when they do it, they get a 5-dimensional potential that looks like something like this, where the n equals 5, so this is the potential for this mode. The n equals 4 theory that we've been dealing with lives up here, which seems kind of unmoving, but as we discussed, if this mode has a negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system on right-molar treatment, and it's okay not to assume it. We know we're in this situation if you go back to the n squared equals delta minus d dictionary, being relevant, that is delta less than d, exactly means being epsilon in supergravity, and you kind of guess what happens. There's some solution where the field, and there's some solution which has here's z equals 0, here's z equals infinity, here's AES region. There's some transition region as you roll down the potential, and then there's a new ADS solution. So this is a particular. This is exactly what the field theory reasoning leads one to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you expect. Yes, sir. Stability is equal to stability is equal to stability. The DF bound is satisfied here, meaning that there's no instability. Tom talked about this too. There is no instability in time, but there's some sense of it's not really instability. But you don't roll down the thing in time because the radiant energy protects you. But you can roll down when you travel in space in the radial direction. Sir. If you see potential like this, you don't expect this to be stable. This solution. That's all I'm saying. And I'm saying that it is stable because I'm not sure the quick infinite is the question. But I'm saying that it is stable because there's also gradient. There's also gradient energy that if you look at time evolution, actually, in terms of potential. I'm saying zero gravity theory. In zero gravity theory, you have this is the potential in the gravity theory. Sorry, this is the potential in the gravity theory, and when you look at the radial equation, there are solutions which start here and end up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. With two masses, the same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular steady solution. But it doesn't have a singularity because then you look at it carefully, you realize that it's a bunch of D3 branes. And so what the geometry is here is that, well, let me draw ADS space, proper ADS space. This way, this is z equals 0 at the boundary, and the spatial things are changing up. And it never gets to z equals 0. It kind of it's a bad way to look at the picture. But the point is that the whole space, see, once you really draw it, the point is that you never get to z equals infinity. The geometry smoothly rounds off. This is actually not the ADS, but the contact direction here. And this is z equals 0, and they smoothly round off at some z equals z max. In terms of the metric, you have this df squared is L squared over c squared, theta mu nu, dx dx nu. And again, in the ADS geometry, one has arbitrary low energy excitations by moving the excitation to smaller and smaller z. That reduces energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that, and so you have a mass cap. So whenever you're trying to perturbate a relative perturbation for the control theory, there's a good chance that all you're going to do is give mass to everything, and on the geometric side, that's reflected by capping off the geometry. Here, though, it works out that you've got this plus you have n minus 1 d3 branes, not n d3 branes, sorry. There's the minus 1 is a distraction, we won't talk about d3 branes. And so the bulk theory exhibits exactly the massless sector that you would expect from the field theory. And the thing about cyber goodness is the whole moduli space, these d3 branes actually have lots of places that they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. Actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking of this years ago, never forget. You know if anybody ever turned it out? Homer problem. Yeah, it's a great question. So part of the problem is that the supergravity folks first had to tell us what the metric is for arbitrary distributions of d3 branes, because this trick gives you special distributions. If they would tell us what was arbitrary distributions, then one could bring it to the argument and find out what is the geometry. You also have a nice geometry picture of the district mark. You have something special that happens as you move from Martian. And we don't just understand for yourself as well. Okay, right. You said we understand that for small number, it might not be in the geometric regime. Good. Okay, with three masses, you try again the same trick. That is, you get some potential, you follow it off. The 5-dimensional solution you get lifts to a singular 10-dimensional solution. Question? Yes. A good question. This consistent truncation magic chooses a particular point in the moduli space. And of course, if that's the point in the moduli space, I mean, the consistent truncation is a solutionary thing that doesn't capture everything. For a while, it was a goal to try to find the gravitational description of the general point on the moduli space. But it seems to be beyond the supergravity. You don't have to be there, but actually describe the that reaction of these three grains. It seems like an open question. The person who was the most repulsive were, and they pushed on the problem, made some progress, but I don't think they ever gave a general solution. It's not smooth when the fields run up to infinity. It's unique that it's a recipe. They look at the radical equation, and it's a trick. And it's a trick which is one-to-one in the way it's used now. Yeah. But in fact, when you get three masses, this becomes even stronger because let me see what happens with three masses. With three masses, you can do the same thing. The five-dimensional thing blows off. You have a single 10-dimensional solution, but it's not any recognizable, sensible brain. No, this is in 2B, so there's no 11D left. Yeah, well, the two masses are really just D3 brains. Let me finish this, telling you what happens with three masses. So three masses, if you're Max Strassler, you look at the game theory side of the duality for inspiration. If your superpotential is, W is M alpha, then the bone mass equals, say, phi alpha squared, plus, alpha beta gamma, commutator phi alpha, phi beta, phi gamma is all traced. Then I'm leaving off the constants. Then the F-term equations tell you that, again, I'm leaving off the constants. M phi alpha is epsilon alpha beta gamma, commutator phi beta is phi gamma, which is to say that you have vacua, but for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2. One phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Coulomb behavior. Remember that the scalar parts of these superfields arose as the coordinates of the D3 branes, and this is saying those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Bob Myers explained that when you put D3 branes in a transverse flux, it's considered favorable for the coordinates to become non-commuting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with three masses is that it ends on, it actually ends on a D5, or an S5, or in fact, some many 5 branes. And the fact that there are many ways to calculate the geometry reflects the fact that the theory has many vacua. And so there's a nice match between you see you're doing several things, but there's a nice match between theory and expectation and what the gradient tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry does, and in particular it's useful to have insight from the gauge theory as well. By the way, once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brain. It was smearing the 5-dimensional object out into like a 6 or 7-dimensional object. And so it was trying very hard to get the right answer. Okay. Now, the last thing I want to say about, I'm pretty much on schedule. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So, one of the things I'd like to talk about is to measure the potential between a source of coordinate anti-quark fundamental, that maps of the QQR potential. Fundamental. There are fundamental, you can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it in going back to Gust and Wilson, is thought to be the color electric flux tube. And one could say more to justify this, the time is short. The way you calculate potential is to consider a string hanging down from the boundary, and then subject to suitable renormalizations, the potential is just the tension of that string. Again, the potential is the total energy of that string coming from its tension. Now, the tension, the effective tension, so again, this is the Z direction, is the local tension times the translation, the gravitational relationship, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further it hangs. And in fact, in ADS phase, you don't argue much yet, because just by its scale varies as messing units. As you pull the ends further apart, the string hangs down lower, and so it can produce energy and in such a way that the potential goes one above it much by symmetry. The coefficient is interesting, but no time for that. In a confining vacuum, on the other hand, we have this idea that there's some Zmax. And so, this is a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the ends further and further apart, and most of this thing is just running along the bottom of the space at the largest value of Z, the different values you can get. And so the effective power of the string is just, it's not zero. It confines. And that's what happens with three masses. With two masses, the subways that are not confining, they're homomorphic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the two masses, but there's also the D3 branes. And so now I'm going to draw the same picture. So here's G equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those D3 branes. So I'm looking now from the perspective that sees the three directions more explicitly, and so here's your D3 branes sitting at the bottom of the space, and the strings hang down. But once the string ends on the D3 brane, it doesn't go, it stores its flux. But the flux is just a U1 gauge field, and it's free to spread within the D3 brane. So you get a Coulomb potential for a different reason than you did in the ADS space, but it's still Coulomb. So the general thing with D3 proceed with just going to lower this one, because it's often hard dimensional, ends on hard dimensional. It doesn't just end, there's always some, the arrows running the other way, there's always some flux carried by these objects, which has to somehow run through the hard dimensional object. But again, because the three branes have a really gauge field, the flux can spread freely. Okay, so that's the general idea of RG flows and also some specifics. Yes. You've got strings, you have D strings, and you have DQ bound states. So you have the entire sort of SL2Z multiple objects. So in fact, with all of these phases, you also want to ask about the loop, the stages of the magnetic, essentially magnetic objects. Are they confined? Are they Coulomb mechanisms? There's always an analogous story for those. And similarly, you can ask for external dynamic sources. Yep. Some CFTs have operators in the range between the minimum allowed by sort of unitarity, like full algebra, and half the dimension of the space of the CFT. And this is the regime where, as we said, you have to take the alternate boundary condition, the less obvious one, on the scalar field at Z equals 0. But this is also special for another reason. It's special because 2 delta is less than Z. And so the double trace operator squaring the original operator is relevant. Now, again, I'm using here large N factorization. In the large N limit, the amplitudes of the two operators at a point, and they're each connected to the rest of the graph, but the leading and amplitudes are fully disconnected between the two operators, and so its dimension is just twice the original dimension. And so we want to see where this goes, and it's an interesting story. So, for a couple of reasons. So, let's perturb. So we have our generating functional for the original CFT, and now we're going to add to it a double phase perturbation. And the nice way to think about this is to introduce an auxiliary field. And so understanding where this theory goes to isn't going to be so hard, because we can just use this trick to rewrite it in terms of the theory we know more about, the theory with just single phase operators per time. And this is, in fact, just by the usual definition. W equals sigma, E is the minus 1 over 4G, and then the usual T for J plus sigma. Just the generating functional for the single phase correlators. Okay, now we can now do the sigma integral in a large N limit. We can now do the sigma integral just by saddle point. We can just find its saddle point. And actually, what this probably is the right answer beyond large N, but let's keep things simple. So let's evaluate my saddle point, and the saddle point is at 1 over 2G sigma. The saddle point is at 1 over 2G sigma equals partial Z, partial sigma, which but this is just the generating functional. So you're differentiating one with respect to the source, just pull down the expectation value. And if we go back to our original dictionary, a given operator in the CFT is just the normalizable mode of the quantized mode of the quantum field of the bulk. And so this is alpha, the quantized mode, as a function of beta equals J plus sigma. The fixed mode is set to these values, and then you evaluate the quantized mode. And if we now plug in, rewrite what we have here is that 1 over 2G, actually there's what if I C sub O's here? Some constant. 1 over 2G, beta minus J is equal to C sub O alpha. So what you see is that introducing double phase perturbation is equivalent to introducing a boundary condition of this form. And there's some concepts that are so interesting. And forget J for now, which is just again a source we're using to the generating function. The basic statement is that we now have a generalization of the previous boundary conditions, where instead of 1 of alpha and beta being set to 0 or to a fixed value, they are proportional to each other with some constant proportionality. And we can now figure out, so now we can write it, let me get into the J, it's just again, this generating function, so to keep things simple. We now have, we can now write the mode expansion that phi is alpha Z to the, to the Z minus delta plus beta Z to the delta. We're in the regime where delta is less than D over 2, so this is the larger mode of the boundary sorry, wait, that's right. This is the larger Rosette boundary, this is the smaller Rosette boundary. But the point is, if alpha and beta are now both turned on, there's just some constant proportionality between them, so I can make one of these, I can write one of these in terms of the other constant. This is one linear combination, one definite linear combination of these two terms turned on. And the point is now that if you go to and it looks like the alternate quantization, the one that we started with in the UV to get that range of dimensions, but in the IR, this mode is the one that dominates, and it looks like the usual quantization in which delta, the effective density operator, is now changed to the minus delta. So what this is describing is a flow between the two possible boundary conditions for the given, well, mass squared is a flow. So we call the alternate quantization, that is quantization in which you have an operator whose dimension is in that range. That happens. There are other operators in the N equals 4 theory, but in many variants of the N equals 4 theory, you do have operators whose dimensions are in that range. But in fact, as a sort of point of naturalness, that's unnatural, because if you turn on the double phase perturbation with even a small coefficient, the system will flow to the other solution with the operator moves up the larger dimension. And this has some relevance to the model of very liquids that Han was talking about, where you have various flows going on in the theory. This example also exhibits another idea that's worth remembering, which is that if you look at say the second line there, the second line, we've taken the original AES CFT theory, and we've added a field sigma that couples to an operator from CFT. And this is an auxiliary field. Its action is just this local sigma squared. But you can imagine generalizing the structure and coupling fields in, whereas in a sigma squared you have some typical Klein-Gordon action or some kind of non-trivial dynamic action. You could take any operator on interact action. And what does this mean? What this means in this case is that your Lagrangian theory has two pieces. It has a strongly coupled piece, and it has another piece which may be coupled as just an equivalent Lagrangian. And the strongly coupled piece has a gravity solution. These two pieces are coupled together through some interaction like that sigma O up there, some bilinear interaction. And so you get this kind of semi-holographic, where you have a strongly coupled piece and you're using gravity to solve the strongly coupled piece, and then you're coupling that solution to an explicit Lagrangian description of the other part of the theory. And again, this semi-holographic idea, it's something in a lot of different places. There's no reason you can't basically, you're adding fields to the boundary theory by hand, and there's no reason you can't do that in a definite physical meaning, as I just said. And again, it comes up in these two functions that Han is going to talk about.
So the first line,
it's like in the N equals 4 theory, that's not invariant under the N equals 4 theory, so you wouldn't have it. That cosine doesn't have this operator, but right. So in some cases, if you insist that your starting point preserves supersymmetry, then you don't worry about this. But from kind of a contentionary point of view, you have some UV theory, and you get your most general Lagrangian persistent symmetries, which will usually contain such terms, which means that it's unlikely in this framework to find operators whose dimensions is in that the ultimate range. Well, that happens small. I think that happens small n. So indeed, and of course the real world n is not so large, and so indeed we're talking here about things that happen within this large n universe that may not need to be true small n. Yeah. When it's small n, the distinction between single trace and multi-trace begins to break down. When you get n equals 1, there's no distinction at all. When you get n equals 2, you've got single and double trace, but then double trace are redundant. So the whole distinction of single trace and multi-trace is sharpest in the 1 over n expansion.